AC machines are generators that convert mechanical energy to AC electrical energy, and motors that convert AC electrical energy to mechanical energy. The fundamental principles of AC machines are very simple, but unfortunately they are somewhat obscured by the complicated construction of real machines. There are two major classes of AC machines: synchronous machines and induction machines. Synchronous machines are motors and generators whose magnetic field current is supplied by a separate DC power source, while induction machines are motors and generators whose field current is supplied by magnetic induction, similar to that of a transformer action, and it is transferred into the field of the windings. The field circuit of most synchronous and induction machines are located on their rotors. We will start our study of AC machines again with a simple loop of wire rotating within a uniform magnetic field. A loop of wire in a uniform magnetic field is the simplest possible machine that produces a sinusoidal AC voltage. This case is not representative of real machines, of course, since the flux in a real AC machine is not constant in either magnitude or direction. However, the factors that control the voltage and torque on the loop will be the same as the factors that control the voltage and torque in a real AC machine. This slide shows a simple machine consisting of a large stationary magnet producing an essentially constant and uniform magnetic field and a rotating loop of wire within that field. The rotating part of the machine is called the rotor, and the stationary part of the machine is called the stator. We will move the rotor between the magnets and turn it so that we are looking at the loop on the end, that is A, B, and DC. We will keep a top-down view of the rotor in the upper right-hand corner as well in order to just visualize what is actually happening a lot easier. If the rotor of this machine is rotated, a voltage will be induced in the loop of wire. The loop of wire shown is rectangular with sides A, B, and CD perpendicular to the plane of the page, and with sides BC and DA parallel to the plane of the page. The magnetic field is constant and uniform, pointing from left to right across the page. We will consider the rotor a single loop rotating counterclockwise at an angular speed of omega. The radius of rotation we will call r. To determine the total voltage, call it E subscript tot, on the loop, we will examine each segment of the loop separately and sum all the resulting voltages. The induced voltage on each segment is given by the equation: the velocity times the magnetic flux density times the length of the wire segment. Let's move the loop coil over here in order to unclutter the vectors. For segment AB, the velocity of the wire is tangential to the path of rotation, while the magnetic field B points to the right, as shown here. The voltage on the segment BA is given by the equation V times, or V cross B times L. The quantity V cross B points into the page. This means the voltage vector is the same direction as segment AB, meaning the voltage rises from A to B. Therefore, the induced voltage on this segment of wire is VBL from A to B, where E, we'll call it the induced voltage, B is the flux density, L is the conductor length, or the length of the loop that we're considering, and theta is the angle between the field and the velocity, and V is the conductor velocity. We are going to look at segment BC and DA at the same time because the logic and the results are the same. The induced voltage is given by the equation V cross B times L. Keep in mind that the stator is a three-dimensional object and that the magnetic field between the north and south pole is going to be uniformed over a three-dimensional area, defined by the ends of the north and south poles. Therefore, the magnetic field will appear across our diagram like this. Remember, our loop is rotating such that the end segments of the loop will be rotating about its center point. This means that each part of the segment will be traveling at different velocities depending on the distance from the center of rotation. It also means that the velocity of the outer portion of the segment is moving faster than the inner portion of the segment, so the velocities will look something like this in the first half of the segment. The cross product V cross B points into the page, and in the second half of the segment, the quantity V cross B points out of the page. Since these two half segments are induced with an equal and opposite voltage, then the sum of both is zero. Therefore, the voltage in both segments will equal zero. For segment CD, the magnetic field B points to the right as shown here. The voltage on the segment end is given by V cross B times L again. The quantity V cross B points out of the page. This means that the voltage vector is the same direction as segment CD, meaning the voltage rises from C to D. Therefore, the induced voltage on this segment of wire is V times B times L from C to D. Therefore, the induced voltage on this segment of wire is V times B times L out of the page, where again E is the induced voltage, B is the flux density, L is the conductor length, theta is the angle between the flux density and the velocity, and V is the conductor velocity. Note, this angle is equal to the same angle found in the segment BA plus 180 degrees. This means that sine theta is equal to sine theta plus 180 degrees. This essentially means we only have to deal with the acute angle theta. The total induced voltage in the loop, we'll call it E, or the EMF, subscript IND, is the sum of the voltage on each of the segments. And we'll call it EBA plus ECD plus EDC plus EAD. Substituting in our equation values, and adding them up gives us 2 times the velocity of the loop times the flux density times the length of the individual loops AB and or CD, because they're both the same, times the sine theta. And theta is the angle at which the loop is at any particular time as it rotates with an angular velocity of omega. The resulting voltage is shown as a function of rotational angle, and it looks very sinusoidal as you see here. There is an alternative way to express this behavior. If the loop is rotating at a constant angular velocity omega, then angle theta of the loop will increase linearly with time t. In other words, theta can be expressed as omega times t. And our angle is, in this case, in radians. Also, the tangential velocity v of the edges of the loop can be expressed as this equation: v is equal to the radius times the angular velocity omega, where r is the radius from the axis of rotation out to the edge of the loop, and omega is the angular velocity of the loop. That means we can rewrite the equation substituting r omega for v. Notice also from the diagram that the area A of the loop is just equal to 2 times r times L. Therefore, the induced voltage can now be equated to the area times the flux density times omega times sine omega t. Finally, note that the maximum flux through the loop occurs when the loop is perpendicular to the magnetic flux density lines. This flux is just the product of the loop's surface area and the flux density through the loop, B. Therefore, the final form of the voltage equation for the induced voltage is the maximum flux times omega times sine omega t. Thus, the voltage generated in the loop is a sinusoid whose magnitude is equal to the product of the flux inside the machine and the speed of rotation of the machine. This is also true of real AC machines. In general, the voltage in any real machine will depend again on these 3 factors: the flux in the machine, the speed of rotation, and some constant representing the construction of the machine, and which includes the number of loops, etc. Now assume that the rotor loop is at some arbitrary angle with respect to the magnetic field, and that a current is flowing in the loop, as shown here. If a current flows in a loop, then a force will be induced on each segment of the loop perpendicular to the flux field, given by the equation F is equal to I times the quantity L cross B, where B is the flux density, L is the conductor length, and it is assumed a vector with the same direction that of the current, and I is the current. The torque on each segmental loop will then be given by tau times the force applied times the perpendicular distance. R is the radius from the axis of rotation center out to the edges of the loop. Also, the angle of the plane of the single loop rotor with the force vector F is theta. The direction of the torque is clockwise if it would tend to cause a clockwise rotation, and counterclockwise if it were tend to cause a counterclockwise rotation, as in this case. Segment AB, in this segment, the direction of the current is into the page, while the magnetic field B points to the right. The induced force on this segment of wire is given by this equation. F is equal to I times L cross B. The segment is 90 degrees to the magnetic field, so the force is given by the current times the length of the segment times the flux density down. The resulting torque is the force applied times the perpendicular distance to the center of rotation, which is given by this equation. Tau is equal to F times R sine theta, or RLB sine theta clockwise. Segment BC. In this segment, the direction of current is in the plane of the page, while the magnetic field B still points to the right. The quantity L cross B points into the page. Therefore, the induced force on this segment of the wire is ILB into the page. For this segment, the resulting torque is 0, since vectors R and L are parallel and the angle between them is 0, since sine 0 is equal to 0, then the torque is going to be 0 for this segment. Segment CD. In this segment, the direction of the current is out of the page, while the magnetic field B points to the right still, and the induced force on this segment of wire is down, given by the equation F is equal to I times the quantity L cross B. The segment is 90 degrees to the magnetic field, so the force is just I times L times B up. The resulting torque is the force applied times the perpendicular distance to the center of rotation, which is given by this equation. Tau is equal to force times R times sine theta, or note this angle is equal to the same angle found in segment BA plus 180 degrees. This means that sine theta is equal to sine theta plus 180 degrees. This essentially means we only have to deal with the acute angle theta, which says the equation now is equal to RLB sine theta clockwise. Segment DA. In this segment, the direction of current is in the plane of the page while the magnetic field B still points to the right. The quantity L cross B points into the page, therefore the induced force on this segment of wire is ILB, into the page. For this segment, the resulting torque is 0 since vectors R and L are parallel, and the angle between them is 0, and sine of 0 is equal to 0. Therefore, the torque for this segment, dA, is going to be 0. The total induced torque on the loop is T, I'm calling it T subscript IND, is the sum of the torques of each of its individual sides. Which, if we plug in the formulas that we have just calculated, gives us this. And adding up the quantities, the result is the torque is given by 2 times R times I times L times B times sine theta. The resulting torque is shown as a function of rotor loop angle. Note that the torque is maximum when the plane of the loop is parallel to the magnetic field, and the torque is 0 when the plane of the loop is perpendicular to the magnetic field. There is an alternative way to look at this situation which clearly relates the behavior of a single loop of wire to the behavior of a larger real AC machine. If we establish a current in the loop as shown, as we did previously, the current will generate a magnetic flux density B, and we'll call it B subscript loop, with the direction shown here. The magnitude of B loop will be given by I divided by G, where G is a factor that depends on the geometry of the loop. Remember that when a current flows in the loop, that the torque will be induced on the loop given by this equation. Because B loop is equal to I divided by G, then we can substitute G B loop for I, giving us that the torque is given by 2 times R times G times B loop times L times B of the stator times sine theta. Also note that the area of the loop is just equal to 2RL. Substituting our equation yields the result that the induced torque will be A times G times B loop times B stator times sine theta, where AG is a factor depending on the construction of the machine. B stator is used for the stator magnetic field to distinguish it from the magnetic field generated by the rotor, and theta is an angle between B loop and B stator. The angle between B loop and B stator can be seen by trigonometric identities, which we won't go into right now, to be the same as the angle between the force vector and the rotor angle. Thus, the torque induced in the loop is proportional to the strength of the loop's magnetic field and the strength of the external magnetic field, and the sine of the angle between them. This is also true of real machines. In general, the torque of any real machine will depend on the following four factors: the rotor magnetic field, the external magnetic field, the sine of the angle between them, and a constant dictated by the construction of the machine. We have shown that if two magnetic fields are present in a machine, then a torque will be created which will tend to line up the two magnetic fields. If one magnetic field is produced by the stator of the AC machine and the other one is produced by the rotor of the machine, then the torque will be induced in the rotor, which will cause the rotor to turn and align itself with the stator magnetic field. If there were some way to make the stator magnetic field rotate, then the induced torque in the rotor would cause it to constantly chase the stator magnetic field around in a circle. This is the basic principle of all AC motor operations. What you see here is part of the patent paperwork for Nikola Tesla's induction motor. Notice the date on this patent. It's May 1st, 1888. Tesla's work was done over 165 years ago, and it is still relevant to today. I could have just redrawn the stator and not had any reference to Nikola Tesla, but I thought it interesting to note that this guy was way ahead of his time, and some of his patents are still in vogue today. So I'm going to use his polyphase motor that you see here, and we'll analyze it and keep in mind that it's still relevant today. Since this lesson is about rotating magnetic field in the stator, my first step will be to remove the rotor from this diagram. That done, we can trace the wires to show which coils are connected together, and it will be clear that there's a north and south pair and an east and west pair. Notice also that these two coil pairs are situated at 90 degrees to each other. We say that they are mechanically separated by 90 degrees. The key to most alternating current machines is the rotating magnetic field. A rotating magnetic field is produced in many different ways. The easiest way to understand how a rotating magnetic field is produced is by looking at two alternating current sources being applied to the stator you see here. Let's start with a north and south pair of coils, and we are going to attach a sinusoidal current generator to this pair of coils. It could be an AC voltage generator, but we are only interested in current that is produced in the coil pairs, and ultimately we want to look at current. So we'll connect a current source to these pair of coils. The magnetic field or flux density that is produced between the two coils, which at all times is directly proportional to the current. The AC current connected, and ultimately the magnetic field is going to be described in the time domain by this equation. B is equal to sine omega t, where B is the flux density, T is time, and omega t is the angle, and omega is the angular velocity. At T is equal to 0, B, the flux density, starts at 0, goes to a maximum, returns to 0, then goes negative to a maximum and continues to repeat itself. This current produces a magnetic field in the vicinity of the rotor that we will represent by a phasor whose magnitude follows that in the time domain. It is in one direction only, between the red plus of the stator. I'm going to represent the magnetic flux by a vector or a phasor that goes with the current to a maximum, then to a 0, then to a negative maximum, back to 0, and continues to repeat itself. But the phasor of this magnetic field is in a singular direction only, albeit positive or negative or up and down. Looking at the east-west pair of coils, it is also connected to an oscillating current generator, but this one is described as B is equal to cos omega t, which is important because at time 0, the current is at a maximum and it produces a magnetic field in the vicinity of the rotor that goes east and west, but starts at 1, reduces to 0, goes to -1, back to 0, goes up to maximum again, and repeats itself. But the phasor of this magnetic field is in a singular direction, only it goes positive and negative, left or right. Now, let's put these all together, and what you see is two pairs of coils, one north and south, which I have colored red, and the other east and west, which I have colored blue. We saw that they are 90 degrees physically separated from each other, so we say that they are mechanically separated by 90 degrees. Also remember that we excited the red or north set of coils by a sinusoidal current, sine omega t, which starts at 0. The blue coil pair, east and west, is being excited with a cosine current, cosine omega t, that starts at time equals 0 at a maximum. We say that these two coils are electrically separated by 90 degrees, which I am showing in the upper right hand corner in the time domain. Now, the magnetic field is proportional to the current that is flowing in each of these coils. But remember, we are going to be looking at the vector sum or the phasor sum of these two magnetic fields. And it's going to be the resultant. I'm going to color green, but it's going to be the vector or phasor sum of the red plus the vector or phasor sum of blue. But those two functions are phasors or vectors, and when added, they have to be added with the rules of adding vectors. And I'm going to draw the vector fields in the area of the rotor And remember, these are magnetic fields that are produced by the current flowing in the coils that are 90 degrees mechanically separated and 90 degrees electrically separated, and the sum of those two vectors will produce the resultant field vector that will be rotating as indicated by the green phasor. Notice that the two field vectors are not rotating. That is, the blue and the red vectors are not rotating, but they are pulsing back and forth to a maximum, plus maximum, negative maximum. However, the resultant, the green phasor, was a rotating vector. So let's take a closer look at these and do the math just to verify that I wasn't performing some type of magic in front of you here, that those two north and south, east and west electrical magnetic fields actually produce a rotating magnetic field when summed together. So we had a look at the vectors, including the resultant vector, which the vector sum of the two coil fields, and it certainly looked like it was rotating. However, just to prove that isn't some type of trickery that I've done, let's look at some key points in the cycle and input currents. Starting at point where t is equal to 0, or the time at the beginning, the red current is at 0, so there will be no displacement or field in the north-south direction. However, there will be a very strong field in the east-west due to the blue field current, so the vector sum is from cos omega t only, so the current flowing in the blue phase is producing the resultant vector green, and it will be at the same magnitude as the blue one, because that's all it's summing up, as the field vector in the blue coil. Now, let's move down in time to where omega t is at 90 degrees. At 90 degrees, the blue current is 0 and the red current is at a maximum. So cos omega t will be 0 and the resultant magnetic field will be caused by sine omega t. So the red field will be showing straight up and down, or straight up in this case. The resultant green field will also be straight up, because the only contributor to the sum is the red magnetic field. So you can see that the resultant field looks to be rotating, or it has rotated through 90 degrees. If we look at a time where omega t is 180 degrees, then sine omega t is at 0 and cos omega t is at -1. So the resultant field will be all made up of cos omega t, which happens to be in the minus direction, which is to the left, giving us a resultant field vector of the same magnitude in the same direction. Now, if we take a look at 270 degrees, in other words, omega t is equal to 270 degrees, cos omega t is 0 and sine omega t is equal to -1. And the field will be made up of only sine omega t exclusively, which is pointing straight down. And the resultant magnitude will also be straight down. So these key points are showing us that although the blue field is going left and right, and the red field is going up and down, the resultant green field seems to be rotating at least as indicated by these 4 points. Let's take a look at one more point, and that is where omega t is equal to 45 degrees. So we want to find the green resultant phasor, which is the sum of the B red plus the B blue. These two values are vectors. B sine omega t is a vector that varies up and down. In this case, it's up, but not at a maximum. B equal to cos omega t is a vector that varies right and left, and when adding these two quantities together, we have to use the rules of vector addition, which means in order to find the resultant, or the green vector at any time or angle, we have to square cos omega t and sine omega t, then add them together, and then find the square root in order to come up with the resultant answer. The green resultant is the sum of sine omega t plus cos omega t. We know that a 45-degree right-angle triangle is a special triangle that has its sides in the ratio of 1, 1, and the root of 2. So sine of 45 is 1 over root 2, and the cos of 45 is also 1 over root 2. To calculate the resultant field magnitudes, we square both these two and add them and find the square root of the result. And that will give us the magnitude of the resultant field or green vector. If we square 1 over root 2, we'll end up with 1/2. So underneath the square root sign, we just have 1/2 plus 1/2, which we can take a step further, and we know that this is equal to 1. And in actual fact, if you remember your trig identity, the Pythagorean trig identity, where sine squared omega t plus cos squared omega t is equal to 1, then it would have saved us a little bit of calculations here. However, the takeaway from this is we have a position 45 degrees halfway between 0 and 90, and you can see the vector is halfway between 0 and 90. It's at an angle of 45. And the other takeaway is the magnitude of the resultant is 1. So we can see from the plots that we calculated that the magnitude of the resultant vector is going to be 1. And if we remember our Pythagorean trig identity, it's always going to be 1. And in actual fact, as it rotates, it's going to rotate at the same frequency as the electric frequency of the blue phasor and the red phasor. We'll be looking at this rotating field as well as a rotating field in three-phase circuits a little bit later on. However, you can see that in what they call a polyphase motor, in this case it's a two-phase motor, that we have a rotating field. And the key here was positioning 90 degrees mechanically and electrically 90 degrees. Let's continue to look at the Tesla motor. We have so far studied the stator, and we would now like to have a look at the rotor and see what's happening there. In general, a rotor mounted on a shaft is a hollow laminated core having slots on its outer periphery. The windings placed in these slots, called rotor windings, may be one of the two following types: the wound rotor type and the squirrel cage rotor type. A wound rotor consists of a laminated cylindrical core. The rotor winding is uniformly distributed in the slots. The open ends of the rotor winding are brought out and joined to an insulated slip ring mounted on the rotor shaft, with one brush resting on each slip ring. The brushes are connected to a rheostat. At the starting, the external resistances are included in the rotor circuit to give a large starting torque. These resistances are generally reduced to zero as the motor runs up to speed. The external resistances are used during the startup period only. When the motor attains normal speeds, the three brushes are short-circuited, so the wound rotor then runs like a squirrel cage rotor. A squirrel cage rotor consists of a laminated cylindrical core having parallel slots on the outer periphery of these parallel slots. One copper or aluminum bar is placed in each slot. All these bars are joined at each end by a metal ring called an end ring. This forms a permanently short-circuited winding which is virtually indestructible. The entire construction, bars and end rings, resembles a squirrel cage, hence the name. The rotor is not connected electrically to the supply, but has currents induced in it, such as in a transformer action, from the stator. Those induction motors which employ squirrel cage rotors are called squirrel cage induction motors. Most single and three-phase induction motors use squirrel cage rotors, as it is remarkably simple and robust in construction, enabling it to operate in the most adverse circumstances. However, it suffers from the disadvantage of a low starting torque. It is because the rotor bars are permanently short-circuited, and it is not possible to add external resistance to the rotor circuit to have a large starting torque. When a polyphase supply is connected to an induction motor, such as we see here, it is made up of more than one phase. However, the frequency of those two phases must be identical. In this case, we have two supplies connected whose frequency is equal to omega. They may be out of phase, which they are by 90 degrees in this case, but they are still supplied with the same frequency. The frequency described by F is usually in hertz or cycles per second, whereas The term omega can be either cycles per second or radians per second. Both are frequency and convertible by the equation 1 cycle per second is equal to 2 pi radians per second. A rotating frequency, when generated, rotates at what we call synchronous speed, and it is designated as n subscript s. The speed described by n is usually in RPM, or revolutions per minute, and in this case of a two-poled machine, it will be the same as the direct proportional frequency to the supply. But remember that the frequency of the supply is in CPS, cycles per second, or RPS, radians per second. So when comparisons are required, in other words, when equating the RPM to CPS or RPS, these conversion equations are required. RPM equals 60 CPS equals 120 pi RPS or radians per second. Another thing to be aware of is the pole count in a machine. A machine is described as having a set number of poles. A pole of a machine is the magnetic pole created by the coil windings. There is always a north and south pole created, which in the pole count equates to 2 poles. Furthermore, the pole count is the number of poles per phase. In this case, there are 2 phases, sine omega t, the red phase, or cos omega t, the blue phase. And there are 2 poles per phase, so the number of poles in this machine is 2. When the rotor turns, it is always described in terms of RPM, or revolutions per minute. Let's zoom in and take a closer look. A rotating magnetic field is set up which rotates around the stator at what is defined as synchronous speed, or n subscript s. The rotating field passes through the air gap and cuts the rotor conductors, which as yet are stationary, and due to the relative speed between the rotor flux and the stationary rotor, EMFs are introduced in the rotor conductors. Since the rotor circuit is short-circuited, currents start to flow in the rotor conductors. Current appears in the rotor conductors due to the rotating magnetic field produced by the stator. Consequently, mechanical forces act on the rotor conductors. The sum of the mechanical forces on all of the rotor conductors produce a torque which tends to move the rotor in the same direction as the rotating field. The fact that the rotor is urged to follow the stator field, that is, the rotor moves in the direction of the stator field, it can be explained by Lenz's law. According to this law, the direction of the rotor currents will be such that they will tend to oppose that which is causing them. Now, the cause producing the rotor currents is the relative speed between the rotating field and the stationary rotor conductors. Hence, to reduce this relative speed, the rotor starts running in the same direction as the stator field and tries to catch it. Let's zoom out for a moment. I'm going to represent the magnetic field with one green phasor arrow, which is rotating in the air gap at a speed of n subscript s, synchronous speed. the rotor rapidly accelerates in the direction of the rotating field. In practice, the rotor can never reach the speed of the stator flux. If it did, there would be no relative speed between the stator field and the rotor conductors, no induced rotor currents, and therefore no torque to drive the rotors. The friction and windage would immediately cause the rotor to slow down. Hence, the rotor speed, N, is always less than the stator field or the synchronous speed, N subscript S. This difference in speed depends upon the load on the motor. The difference between the synchronous speed Ns of the rotating stator field and the actual rotor speed N is called slip, and it is sometimes called slip speed. It is usually expressed as a percentage of synchronous speed. That is, S, the percentage slip, is equal to Ns minus N all over Ns times 100%. When a rotor is stationary, that is, when N is equal to 0, the slip then is equal to 1 or 100%. Now let's look at the induced voltage and hence the current inside this rotor. Previously, we discovered that the induced voltage in a coil that was rotating inside a magnetic field was given by this equation. The voltage induced is equal to phi max omega sine omega t, where EIND or E subscript IND was equal to the induced voltage, B was the flux density, and omega was the angular velocity in radians per second. This equation is valid for the relative movement of a coil inside a magnetic field. It will also be relevant for a moving field on a stationary coil, as in this case. When the motor is first energized, the induced frequency of the voltage is equal to omega radians per second. But as you saw in the previous slide, the rotor will start to rotate, trying to catch up to the rotating field. Let's now look at the rotor and the rotating field after it has reached a steady state condition. I have placed a red marker on the rotor so it will be easy to track the relative motions. And I've slowed down the process in order to visualize the slip a little bit better. This demonstrates the slip of the rotor very succinctly. You can see that the rotor speed is very close to the rotating speed of the field. If the speed of the rotating field were ns and the speed of the rotor is n, then the relative speed is n primed, which is equal to n subscript s minus n. Looking at the frequencies only and not the magnitudes, in the time domain, the rotating magnetic field would look like this. Ns, or n subscript s, is in RPM, which equals 60 times omega, where omega is in cycles per second, or 120 pi times omega, where omega is in radians per second. The rotor angular velocity, n, in RPM, is slightly behind the rotating magnetic field. The difference in the speed of the rotating magnetic field and the rotor will produce a current flowing in the rotor bars. That current in the time domain would look like this, which is hard to see because it's stretched over a longer period of time. So I'm going to compress the time span, and we see that the current frequency is very slow in the steady state condition compared to the rotating magnetic field or the rotor. In terms of RPM, the difference is expressed by this equation. N primed is equal to N subscript S minus N in RPM. But we are more accustomed to expressing frequency as radians per second. The frequency of the current induced in the rotor bars is given by omega prime, which is equal to N prime divided by 2 pi radians per second. In terms of a synchronous speed and rotor speed, omega prime is equal to ns minus n all over 120 pi. Now remember that slip is described as ns minus n all over ns. Therefore, the frequency equation can be rewritten in terms of slip, which equates it to S times ns all over 120 pi. I'm going to replace all but the slip term S using the equation for the rotating magnetic field, where omega is the rotating frequency of the magnetic field, synchronous frequency, which I can mathematically rearrange to make it in terms of the synchronous frequency. So the induced current frequency can be written like this. Slip times omega, meaning that the current frequency is the slip times the synchronous frequency. From our previous slide, we know that the induced voltage is given by the equation E subscript IND is equal to phi max omega sine omega t at startup when the slip is equal to 1. And at any slip, the induced voltage then is given by the equation phi max times slip omega times sine slip times omega t for slip less than 1. Let's take a look at the rotor itself. It was described before. It is made up of a set of bars that are short-circuited at the ends. Those bars electrically may be represented schematically by an inductor and a resistor. We have seen the voltage drop across the rotor is given by the slip times the induced EMF. The amount of resistance in the rotor may be represented by a lump sum. We will call it R2. The inductance of the rotor, we will call it X2, but it is dependent on the slip frequency and may be represented by the slip times X2, where X2 is the reactance of the rotor at standstill. We can now build the equivalent circuit of this machine, and it would look like this. We've already discussed the elements of the rotor and its voltages. The stator, we've already said, is driven by source voltages that are 90 degrees out of phase, but of equal frequency. Let's look at an example. Consider a 50 Hertz induction motor. It has a synchronous speed of ns, which is equal to 1,500 RPM. That means, at standstill, the relative speed between the stator flux and the rotor is 1,500 RPM. If the full load speed of the motor is 960 RPM, then the slip at 960 RPM is given by this equation, which is 1,500 minus 960 all over 1,500, or 0.36. The relative speed between the stator flux and the rotor is now only 540 RPM. Consequently, the EMF is reduced to, we'll call it E2 at 960 RPM, which is equal to 540 all over 1500 times E2 at 0 RPM, which equals 0.36 times E2 at 0 RPM. And that is the slip times the E2 at 0 RPM. The rotor frequency, that is to say the induced voltage and current of the rotor's frequency, is also reduced in the same ratio to F primed, we'll call it, is 540 over 1500. Where F primed is the rotor frequency and F is the supply frequency, which equals 0.36 times F. Then plugging in the system frequency, we find that the rotor frequency, or the frequency of the voltage and the current in the rotor, is 18 cycles per second. The per phase rotor reactance, we'll call it X2, is likewise reduced by the ratio of 540 over 1500, which is equal to 0.36 times the reactance at 0 RPM. Thus, at any slip S, the rotor EMF per phase is equal to S times E2. The rotor reactance per phase is S times the reactance at 0 RPM. And the rotor frequency is the slip times the system frequency, where E2 and X2 are the corresponding values at standstill. Given the rotor circuit at slip speed is S, then the current in the rotor would be S times E2 all over Z2, where Z2 is the combined impedance of the rotor, which is equal to SE2 all over the square root of R2 squared plus SX squared. The rotor power factor is given by this equation. The cosine of phi at slip frequency is R2 all over Z2 at slip frequency, and we'll plug in our values. It's R2 all over the square root of R2 squared plus SX squared. And at standstill, our power factor and our current are given by these two equations, which no longer contain the slip, or if they do contain the slip is equal to 1. This is a plot of the torque versus slip of an induction motor with a rotating field. At the start, the rotor speed is 0, therefore the slip will be 100%. There is a positive torque on the rotor to move it in the direction of the rotating field. The rotor will accelerate and the slip will start to reduce until it gets very close to synchronous speed. As we load the rotor, hence the motor, the load will start to drag on the rotor, slowing it down. As it slows down, the slip will increase, but the torque will also increase until it balances the load. As it is further loaded, the rotor will slip a bit more and the torque will again increase until it balances the load. As it is further loaded, the rotor will slip a bit more and the torque will again increase. However, the maximum load the motor can handle will be at the apex of the curve or the top of the curve. Any load greater than this will cause the motor to no longer have the ability to handle the load. Now remember, the slip greater than 100% or 1 means the rotor is being pushed in the opposite direction. As the name suggests, these motors are used on single-phase supplies. Single-phase motors are the most familiar of all electric motors because they are extensively used in the home appliances and in shops and in offices. It is true that the single-phase motors are less efficient substitute for three-phase motors, but three-phase power is normally not available except in large commercial or industrial establishments. Since electric power was originally generated and distributed for lighting purposes only, millions of homes were given single-phase supply. This led to the development of a single-phase motor. Even where three-phase mains are present, the single-phase supply may be obtained by using only one of the three phases. In this chapter, we shall focus our attention on the construction, working, and characteristics of commonly used single-phase motors. A single-phase induction motor has a squirrel cage rotor and a single-phase winding on the stator. In order to study the single-phase induction motor, I'm going to return to Tesla's induction motor patent drawing. Not that it was patented as a single-phase entity. I only return to it because we're familiar with the construction, and then I'm going to modify it to a single-phase motor. So, I will modify it to suit our needs, only to maintain consistency in familiarization. Single-phase induction motors suffer from a severe handicap. Since there is only one phase on the stator winding, the magnetic field in a single-phase induction motor does not rotate. Instead, it pulsates, getting first larger, then smaller, but always remaining in the same direction. Because there is no rotating stator magnetic field, a single-phase induction motor has no starting torque. A single-phase induction motor is not self-starting, but requires some starting means. The single-phase stator winding, as I said, produces a magnetic field, which pulsates in strength in a sinusoidal manner. The field polarity reverses after each half cycle, but the field does not rotate. Consequently, the alternating flux cannot produce rotation in the stationary squirrel cage rotor. This fact is easily seen from an examination of the motor when the rotor is stationary. The stator flux of the machine first increases, then decreases, but it is always pointing in the same direction, but albeit positive or negative. Since the stator magnetic field does not rotate, there is no relative motion between the stator field and the bars of the rotor. Therefore, there is no induced voltage due to relative motion in the rotor, no rotor current flows due to relative motion, and no induced torque. Actually, a voltage is induced in the rotor bars by transformer action, and since the bars are short-circuited, current flows in the rotor. However, this magnetic field is lined up with the stator magnetic field, and it produces no net torque on the rotor. At stall conditions, or at standstill, the motor looks like a transformer with a short-circuited secondary winding. The fact that single-phase induction motors have no intrinsic starting torque was a serious impediment to early development of the induction motor when induction motors were first being developed in the late 1880s and early 1990s. With the materials and techniques then available, it was impossible to build a motor that worked well. The induction motor did not become an off-the-shelf working product until three-phase power systems were developed in the mid-1890s. However, once the rotor begins to turn, an induced torque will be produced in it. If the rotor of a single-phase motor is rotated in one direction by some mechanical means, it will continue to run in that direction. As a matter of fact, the rotor quickly accelerates until it reaches a speed slightly below synchronous speed. Once the motor is running at this speed, it will continue to rotate even though single-phase current is flowing through the stator winding. This method of starting generally is not convenient for large motors. In order to study this phenomenon a little bit closer, I'm going to spin the rotor in a counterclockwise direction very close to synchronous speed. Synchronous speed omega of the single-phase supply, that is. Assuming that it is still spinning close to synchronous speed, I'm going to take a snapshot which essentially freezes the motion. Because the rotor bars are turning or moving, they are cutting the pulsating field such that, according to Faraday's law, a voltage will be induced in the rotor bars directly below the field poles. It will produce a voltage in one direction in the upper bars of the rotor and in the opposite direction in the bottom bars. I've indicated that with a plus sign and a negative sign. Because the rotor bars are short-circuited by the end plates, that induced voltage will cause current to flow into the page on the top of the rotor, returning out of the page at the bottom of the rotor. Remember, this induced current is only due to the motion of the rotor turning at close to synchronous speed. According to the right-hand rule, the current will induce a magnetic field in the direction to the left, indicated by the blue phasor arrow. Notice that this phasor is 90 degrees with respect to the stator magnetic field. At this point in the analysis, all we have established in regard to the blue magnetic field is that the direction will be to the left, and we know the red phasor direction is up or down. However, both magnetic fields are oscillating. That is to say, the stator phasor we know is oscillating up and down, while the blue phasor, which is momentarily going to the left, is also oscillating left and right. In order to look at the relative timings of these two oscillations, we need to look at them in the time domain. Let's use the stator magnetic field as a reference. That means it will start at 0. It is sinusoidal, and it looks like this. Because it is a reference, we're going to compare all other functions relative to it. We know that the induced voltage in the rotor bars is due to the motion of the bars cutting the magnetic field. That voltage is described by or given by Faraday's law, which tells us that the voltage is equal to minus the change in magnetic flux over the change of time. That means the voltage will also be sinusoidal, but is going to follow the slope of the red curve, which means it's going to be exactly the same shape, but lagging by 90 degrees and starting out at a minus. Now the current in the rotor bars is given by Ohm's law, and the impedance is almost all resistive, so there is no phase shift between the voltage and the current, and it looks like this. The magnetic flux is instantaneously proportional to the current. Since the current is sinusoidal, this means the blue magnetic flux is going to follow the same sinusoidal wave shape. This current is what is induced, or which is inducing a magnetic field that we will describe with a blue phasor. So we know that there are two magnetic fields in the vicinity of the rotor, and their timings will look like this. You should start to recognize this situation. Two magnetic fields with the relative position and timings when added together produce a rotating magnetic field, in this case in a counterclockwise direction. This means that the rotor, once started by some other means, will continue to rotate as long as the single-phase sinusoidal stator field is present. In order to analyze this from a different perspective, I'm going to use something called the double field revolving theory, which we will use to explain this dilemma of no torque at startup, yet torque once the rotor is moved in the either direction. This theory is based on the fact that an alternating sinusoidal flux, and we'll be giving it this formula, phi is equal to phi maximum times omega t, and it can be represented by two revolving fluxes, the magnitude of each equal to 1/2 the maximum value of the original flux, that is phi m divided by 2, and each rotating at synchronous speed in the opposite direction. Consider these two rotating magnetic fluxes, phi 1 and phi 2, each of magnitude phi m all over 2, and rotating in the opposite direction with an angular velocity of omega. Let the two fluxes start rotating from the y-axis at t equals 0. After a time, t seconds, the angle through which the flux vectors have rotated is omega times t. Revolving the fluxes the flux vectors along the x and the y axis, we have the total x component is made up of plus xm all over 2 cos omega t and minus phi m all over 2 cos omega t, which when added together sums to 0. The total y component is made up of plus phi m divided by 2 sine omega t plus another phi m all over 2 sine omega t, which sums to give us phi m sine omega t. Remember, we have only calculated the x and y components. The resultant is found using Pythagorean theorem, which is the square root of the y component plus the square root of the x component. The instantaneous value of the flux due to the stator current of the single-phase induction motor then is given by phi is equal to phi m sine omega t. So this is the mathematics of it. Let's have a look at what it actually looks like, or what is actually happening. Watch this action in relative slow motion. We have a magenta phasor on the right rotating clockwise, and we have an orange phasor on the left rotating counterclockwise. The resultant, when we add them together, is shown in blue along the y-axis. I have recolored the vectors in order that we can follow them a lot easier. The magnitudes of the magenta and orange vectors are 1/2 phi m. So you get a plus 1/2 phi m, then a minus 1/2 phi m along the x-axis, which sums to 0, and you get a plus 1/2 phi m plus another 1/2 phi m along the y-axis, which sums to the blue resultant, which goes plus or minus phi m along the y-axis. As the orange and magenta phasors continue to rotate, the resultant will shrink to 0, then expand to plus or minus along the y-axis. So you can actually see this theory working as the two phasors, orange and magenta, rotate, one clockwise, the other counterclockwise. The resultant will be a pulsating stationary phasor that does not rotate but pulsates. In this case, up and down, minus phi m to 0, then up to plus phi m, and back down again. Consider the case that the rotor is stationary and the stator winding is connected to a single-phase supply. The alternating flux produced by the stator winding can be presented as the sum of two rotating fluxes, phi 1 and phi 2, each equal to 1/2 the maximum value of the alternating flux, and each rotating at synchronous speed in the opposite directions. Flux phi 1 rotates in a counterclockwise direction, and flux phi 2 in a clockwise direction. The flux phi 1 will result in the production of a torque T1 in a counterclockwise direction, and flux phi 2 will result in the production of a torque T2 in the clockwise direction. At standstill, these two torques are equal and opposite, and the net torque developed, of course, is 0. Therefore, a single-phase induction motor is not self-starting. This fact is illustrated in the torque slip curve. Remember that the slip is given by this equation, synchronous speed minus the speed of the rotor all over synchronous speed. The torque due to phi 1 is shown here in magenta and tends to drive the rotor in the clockwise direction. The torque due to phi 2 is shown here in orange and tends to drive the rotor in the counterclockwise direction. A slip greater than 1 or 100% is the rotor turning in the opposite direction to the synchronous direction. And you can see that at standstill, these two torques are equal and opposite, and the net torque developed, of course, is 0. And again, indicating that a single-phase induction motor is not self-starting. So, if we add the two rotating vectors together, we are essentially combining the torque slip curves together, which would look like this. If we were at standstill and applied a sinusoidal current to the single-phase motor, the rotor would not start. Essentially, it would just vibrate, as the torque slip curves here indicate. However, if we gave the rotor a push in the clockwise direction, reducing the slip in that direction, you can see that there will be a torque develop that will continue to push the rotor in the direction in which it was started. As that happens, torque increases and finally gets to a steady state value where no torque is being applied and the rotor will continue to rotate. Keep in mind, if there is no load on this rotor, it would settle out just above 0, but we're assuming there is no load on this rotor for the present time. Now, if we push the rotor in the other direction, a similar thing would happen, only in the counterclockwise direction. As we rotate in the counterclockwise direction, the torque will increase and the speed will increase until we reach close to synchronous speed in that direction. So the single-phase induction motors, as we've stated many times, is not self-starting, and it is undesirable to resort to mechanically spinning the shaft or pulling a belt to start it. To make a single-phase induction motor self-starting, we should somehow produce a revolving stator magnetic field. This may be achieved by converting a single-phase supply into a two-phase supply through the use of additional windings. When a motor attains sufficient speed, the starting means, additional winding, may be removed depending on the type of the motor. As a matter of fact, a single-phase induction motors is classified and named according to the method employed to make it self-starting. Split-phase motors are started by two-phase motor action through the use of an auxiliary winding. Capacitor motors are started by two-phase motor action through the use of an auxiliary winding and a capacitor. Shaded pole motors are started by the motion of a magnetic field produced by the means of a shaded coil around the portion or a portion of the pole structure. So let's take a look at each of these and see what we're talking about. The stator of a split-phase induction motors is provided with an auxiliary or a starting winding in addition to the main or running winding. We'll call it M. The starting winding is located 90 physical degrees from the main winding and operates only during a brief period when the motor starts up, because there is a centrifugal switch that opens the circuit of the starting winding after the rotor reaches about 75% of its final speed. The two windings are so designated that the starting winding, S, has a high resistance and relatively small reactance, while the main winding, M, has a relatively low resistance and a large reactance, as shown in the schematic connection. Consequently, the currents flowing in the two windings have a reasonable phase difference, about 25 degrees to 30 degrees. When the two stator voltages are energized from the same single-phase supply, the main winding carries a current IM, while the starting winding carries a current we'll designate as I subscript S. These two currents sum to a total current from the supply. We'll call it I subscript T. Since the main winding is made highly inductive while the starting winding is mainly resistive, the currents IM and IS have a reasonably phase angle, that is about 25 to 30 degrees, between them, as shown here. Consequently, a weak revolving field approximating to that of a two-phase machine is produced, which starts the motor running. The starting torque is given by this equation, where K is a constant whose magnitude depends on the design of the motor, and we know what IM and IS is. When the motor reaches about 75% of the synchronous speed, the centrifugal switch opens the circuit of the starting winding. The motor then operates as a single-phase induction motor and continues to accelerate till it reaches normal speed. The normal speed of the motor is below synchronous speed and, of course, depends upon the load of the motor. Looking at the characteristics of a split-phase induction motor, we will find that the starting current is 6 to 8 times the full load current. Due to their low cost, split-phase induction motors are the most popular single-phase motors on the market today. Since the starting winding is made up of very fine winding or very fine wire, the current density is high and the winding heats up very quickly. If the starting period exceeds about 5 seconds, the winding may burn out unless the motor is protected by some type of built-in thermal relay. This motor is therefore suitable where starting periods are not frequent. An important characteristic of these motors is that they are essentially constant speed motors. The speed variation is 2 to 5% from no load to full load. These motors are suitable where modern starting torques are required and where starting period is infrequent. In other words, such as driving fans, wash machines, furnace blowers, small machines and tools, etc. You will find that the power rating of these motors is usually between 60 and 250 watts. The capacitor start motor is identical to the split phase motor, with the exception that the starting winding has as many turns as the main winding. Moreover, a capacitor, I've labeled it C, is connected in series with the starting winding as shown in the diagram. The value of the capacitor is chosen such that it leads the main current by about 80 degrees, which is considerably greater than 25 degrees found in the split phase motor. Consequently, the starting torque TS is equal to K Im IS sine phi is much more than that of the split phase motor. Again, the starting winding is opened by the centrifugal action of the switch of the motor when it reaches about 75% of synchronous speed. The motor then operates as a single-phase induction motor and continues to accelerate till it reaches normal speed. Looking at the characteristics of a capacitor start induction motor, although starting characteristics of the capacitor start motor are better than those of the split phase motor, both machines possess the same running characteristics because the main windings are identical. The phase angle between the two currents is about 80 degrees compared to 25 degrees in the split phase motor. Consequently, for the same starting torque, the current in the starting windings is only about half of that of the split phase motor. Therefore, the starting winding of a capacitor start motor heats up less quickly and is well suited to applications involving either frequent or prolonged starting periods. Capacitor start motors are used where high starting torque is required and where the starting period is or may be very long. For example, to drive compressors such as in heat pumps and air conditioners, large fans, different kinds of pumps, high inertial loads. And you'll find the power rating of such motors lies between 120 watts and 7,000 watts. Shaded pole phase induction motors are less complicated than the previous two examples of single-phase induction motors. I'm going to start again with Tesla's patent for the two-phase induction motor, and again I'm going to remove one of the two phases. And I'm going to change it just slightly more by modifying the poles. And in order to see the modification, I'm going to zoom in on one of the stator poles. The same modification takes place on both of the poles, both north and south. The main pole that you see here has a split, and a circular ring of copper is placed around the small split end. The little split end is called the shaded pole. We are looking at the edge of the shading ring of copper that encirculates the shaded pole. This is an approximation of what it actually looks like. As we have seen before, there is an oscillating magnetic field caused by excitation of a single-phase coil. I have indicated the field in the time domain in the upper left-hand corner of the slide. as well as graphically replicating it on the slide as it would appear between the two poles. Of course, because we have zoomed in, we are only seeing the top or the north end of the rise from 0 to maximum back to 0 again. Because this is a changing flux field, Faraday's law tells us there will be an induced EMF in our shaded pole ring that is equal to the changing of the flux. Because this is a changing flux, there will be a 90-degree phase shift between the flux indicated in red and the voltage indicated in blue. Because this voltage is on the ring of copper, a current will flow from positive to negative around the shaded ring. And because the ring is mainly resistive, the current will be in phase with the voltage. The current will create a magnetic flux that is in phase with the current. Zooming out for the moment, what this means is that there will be two magnetic fields set up in the area of the rotor. One due to the single phase supply, which I've indicated in red, and the induced magnetic field between the shaded poles, which I've indicated in blue. In order to better visualize what is happening, I'm going to replace the magnetic fields with red and blue phasors or vectors that will represent the magnetic fields. The actual working portion of the blue magnetic field is one that is perpendicular to the red magnetic field, and it will oscillate with the same frequency as the other blue magnetic field vector. This is a familiar setup that we have already studied with a two-phase induction motor. By introducing the shaded pole, it essentially introduces a second magnetic field that is perpendicular to the original magnetic field to produce a rotating, albeit small, magnetic field in the area of the rotor. This small magnetic field is enough to start the rotor in the direction from the shaded pole towards the unshaded pole, in this case causing a counterclockwise rotation that, once set in motion, like the other single pole induction motors, will speed up and continue to rotate close to synchronous speed. Looking at the characteristics of the shaded pole single-phase induction motors, we will start with the fact that it is of extremely simple construction and does not require a centrifugal switch. These motors are only suitable for low-power applications, such as to drive small fans, toys, hair dryers, desk fans, and that type of thing. The power rating of such motors are in the area of 30 watts and no bigger. And this brings us to the end of the chapter.